Welcome back to the CCA-F Learning Series from BornToSkill. This is Concept 4, Tool Design and MCP Integration, covering Domain 4, which accounts for 18% of your exam. We have now built the foundation. You understand how Agentic AI thinks, when to involve a human, and how to write precise instructions. But all of that thinking and planning eventually has to become action. Today, we answer the question, how does Claude actually reach beyond the conversation and do things in the world? And what makes that reach safe, purposeful, and auditable?
Before we go deep, let us orient you in the course. The CCA-F exam has 5 domains. Our series covers one concept per domain. Domain 1, Agentic Architecture, is fully covered. Concepts 1 and 2 are published. Domain 3, Prompt Engineering, is fully covered. That was Concept 3. You are now watching Concept 4, which covers Domain 4, Tool Design and MCP Integration, 18% of your exam. Domain 5 and its concept on context management come next. A dedicated concept for Domain 2, Claude Code Configuration, follows shortly. Right now, you are here. Let us get into it.
Here is a question that seems obvious on the surface. If Claude is so intelligent, why can't it just search the web whenever it needs to? Most people answer, it lacks internet access. That is true as an implementation detail, but it completely misses the point. The deeper question is not whether Claude can access tools. The question is how that access is designed. Uncontrolled capability is uncontrolled risk. A model that can call any function arbitrarily, without a defined contract, without boundaries, without accountability, that is not a feature. That is a liability. Tool design is not a convenience. It is an architecture decision that determines what an AI system can do, to whom, and with what level of trust.
So let us go to first principles. Why does tool design even need to be a formal discipline? 3 reasons. First, language models are stateless text predictors. They have no native ability to act on the world. No file system, no network, no memory between sessions. Every capability beyond generating text must be explicitly granted by a human through a design decision. Second, granting capability without structure creates chaos. If Claude could call any function arbitrarily, errors would cascade unpredictably. A poorly scoped tool call can delete data, exfiltrate private information, or trigger irreversible changes in a live system. The model has no way to know the consequences unless the tool design tells it. Third, MCP, the Model Context Protocol, is the discipline that fills this gap. MCP defines a standard contract, what tools exist, what they do, what they accept as input, and what they return as output. This contract lets Claude act purposefully, within known and auditable limits. Tool design is the engineering of safe, purposeful, auditable capability for AI agents that must act beyond conversation.
Everything in MCP reduces to 3 building blocks. These are called primitives. The first primitive is tools. Tools are actions Claude can invoke. They are functions with defined inputs and outputs. Claude decides when to call them based on context. Examples, search the knowledge base, create a ticket, send an email. Tools are model-controlled and executable. The second primitive is resources. Resources are data Claude can read. They are structured context exposed to the model, files, database records, configuration. Resources are read-only by design. Claude can access them freely without triggering any action in the world. Resources are application-controlled. The third primitive is prompts. Prompts are reusable instruction templates. They are pre-built patterns the application exposes for common workflows, standardizing how Claude approaches recurring tasks. Examples, a template for diagnosing an issue, or a template for escalating a ticket. Prompts are user-controlled. The key insight, each primitive has a different controller, model, application, or user. This separation of control is what makes MCP systems auditable and safe.
Knowing the primitives is not enough.
You also need to know how to design tools well. There are 4 properties every well-designed tool must have. Property 1, minimal scope. Each tool does exactly one thing. A tool named Resolve Ticket should not also send emails. Single responsibility means predictable behavior. When a tool does too much, Claude cannot accurately reason about its consequences. Property 2, explicit schema. Every input and every output must be typed and described. Claude reads the schema to understand what arguments to pass and what to expect in return. Ambiguity in a schema leads directly to hallucinated arguments. Claude will invent parameters that do not exist. Property 3, idempotency where possible. Read operations should never change state. Write operations should be safe to retry. This makes tool calls recoverable when an agent encounters an error or needs to replan mid-task. Property 4, reversibility signal. Destructive or irreversible tools must be clearly flagged in the description and in the schema. Claude uses this signal to decide when to pause and ask for human confirmation before proceeding. And the anti-pattern to memorize? Avoid what are called God tools. A single tool with 20 parameters that handles multiple use cases is impossible to describe accurately. Claude will misuse it every time.
Now, let us make this concrete. Imagine an AI-powered IT helpdesk agent built on Claude. Users submit support tickets, password resets, network issues, software failures. Claude diagnoses the problem, searches a knowledge base, runs automated diagnostics, applies fixes where appropriate, and escalates to a human engineer when necessary. This agent needs tools. It needs to search the knowledge base. It needs to retrieve ticket history. It needs to run a diagnostic on a user's machine. It needs to apply a remediation script. It needs to update the ticket status. And it needs a safe path to escalate when the problem is beyond its scope. 6 tools, each with a distinct purpose, each requiring careful design. The question is, what happens when these tools are designed well, and what happens when they are not?
Let us look at what breaks when tools are poorly designed. Scenario 1. The God tool. The developer builds a single managed ticket tool that accepts an action string and a parameters object. Claude must guess the correct action. In one session, it calls the tool with action equals delete instead of action equals close. The ticket, along with its entire history, is permanently deleted. No warning, no recovery. Scenario 2. The missing schema. The run diagnostic tool has no documented parameters. Claude hallucinates a target host argument that does not exist in the actual implementation. The diagnostic runs against the wrong machine. The agent returns a confident resolution. The actual problem is never addressed. Scenario 3. No reversibility signal. The apply fix tool can reformat a hard drive under certain conditions. Nothing in its description flags this as destructive or irreversible. Claude applies the fix autonomously on a live production server. There is no checkpoint, there is no recovery path. In every case, the model did not fail. The tool design failed. It failed to communicate scope, schema, and risk to the model.
Now look at what the same tools become when they are designed correctly. The Search Knowledge Base tool has a clear description. Search IT knowledge base articles by keyword. Read only. No side effects. Claude reads this and calls it freely, without hesitation, whenever it needs information. The Apply Fix tool has a description that says, apply a pre-approved remediation script. Warning, irreversible on live systems. Requires confirm equals true. Claude reads irreversible and immediately applies the human-in-the-loop rule from concept 2. It pauses. It explains what fix it intends to apply. It waits for the operator to explicitly confirm before executing. Ticket history and user profile are not tools at all. They are exposed as resources. Read-only context Claude can access freely, with no action triggered. This is the clean separation of read versus act that MCP makes possible. Same agent, same tasks,
completely different risk profile. The behavior is governed by design, not by hope.
Single tools are rarely enough for real-world tasks. Complex helpdesk resolutions require Claude to compose multiple tools in sequence, using the output of one tool as the input to the next. Get the ticket history, search the knowledge base, run the diagnostic, apply the fix, update the ticket status. This is tool chaining, and it is where design quality compounds. A well-named, well-typed tool in the middle of a chain reduces errors downstream. A poorly described tool in step 2 creates cascading misinterpretations through steps 3, 4, and 5. Now, here is the orchestration anti-pattern you need to know for the exam. Exposing too many tools at once. If Claude is presented with 40 tools simultaneously, it spends tokens evaluating dozens of irrelevant options. The chance of selecting the wrong tool increases. Response quality drops. The best practice is to expose the minimum tool set needed for the current phase of the workflow. Orchestrators should gate which tools are visible based on where the agent is in the task. And this is where MCP prompts become powerful. A prompt template can encode the correct sequence of tool calls for a known workflow type, so Claude does not have to reason about the order from scratch each time. The workflow intelligence lives in the architecture, not the model's inference.
Tool design is where everything we have learned in this series converges. From concept 1, the observe, decide, act loop requires act to be well defined. Tools are how act is implemented. The minimal footprint principle from that concept directly shapes tool design. Request only the permissions you need, prefer reversible operations, avoid accumulating capabilities beyond the current task. From concept 2, the reversibility signal on a tool is the direct trigger for human-in-the-loop checkpoints. When Claude sees an irreversible operation, it applies the HITL decision rule. Tool design and HITL design are not separate disciplines. They are the same discipline, viewed from different angles. From concept 3, tool descriptions are prompts. The quality of a tool's name, its parameter labels, its constraint language, all of it determines how accurately Claude will use it. Every principle from prompt engineering applies directly to writing tool schemas. Clarity, specificity, avoidance of ambiguity. Domain 4 is the hinge of the exam. It is where architecture, safety, and language all meet at the point of action.
Let us bring it together in a clean definition. MCP, the Model Context Protocol, is a standard protocol that lets AI agents act on the world through typed, scoped, and auditable interfaces. Capability is granted deliberately, not accidentally. 3 building blocks: tools for action, resources for read-only context, and prompts for reusable instruction patterns. Each has a distinct controller: model, application, or user. 4 properties of well-designed tools: minimal scope, explicit schema, idempotency where possible, and clear reversibility signals. 1 orchestration principle: expose the minimum toolset per workflow phase. Use MCP prompts to encode correct sequences. Avoid God tools. And the connecting thread: tool design is where agentic architecture, human oversight, and prompt engineering all meet. Get it right, and Claude acts with precision and accountability. Get it wrong, and the model's intelligence becomes a liability instead of an asset. That is concept 4, tool design and MCP integration. You now understand the 3 MCP primitives, how to design tool boundaries that Claude can interpret correctly, and why this domain is the architectural hinge connecting everything else in the exam. Next up is concept 5, context management and reliability, domain 5, covering 15% of your exam. We will look at how Claude handles long conversations, maintains coherence across context windows, and signals confidence, the reliability layer that sits underneath everything we have built in this series. If this video helped you prepare, subscribe to BornToSkill for the full CCA-F series. Like the video so others preparing for the exam can find it, and hit the notification bell so you do not miss Concept 5. See you in the next one.